Welcome everyone to another fantastic education session. I'm your host Trevor Matthews, and today is the start of a 5-week series with my friend James Bailey, and we're going to get into sizing software, specifically distribution refrigeration line sizing software, and how to effectively design a system more efficiently, more effectively on a timely manner. James, how you doing, brother?
I'm real good, Trevor. Thank you very much. And hello, everybody. Thanks for taking the opportunity to join. Hopefully, you'll find today's session really useful. As Trevor was saying, this one's going to be a first of a 5-part weekly series. Kicking off with a relatively small system, but as design engineers, it's not all about designing large distributed systems for supermarkets. This one's going to look at a typical cold room application with a couple of room coolers in that are connected to a condensing unit. So I'll be opening and launching White Rose MicroPipe software and going through the calculations with everybody. Hopefully everyone finds it informative.
Yeah.
And I'll kick off with a slide deck shortly, Trevor, as well.
Yeah, that's awesome. Thank you, James. So just a little bit about this 5-part series. So we're going to, like James said, we're going to talk about sizing refrigeration pipework for condensing units for cold rooms. Next week, we're going to get impact of incorrectly sizing refrigeration pipework and how to design a software, how that software removes these problems and how to make it more effective. The third session, we're going to get into sizing refrigeration pipework for maximum energy efficiency. Fourth session, we're going to be diving into the design and the full pipework of a medium-sized convenience store. And the final week, we're going to be designing common liquid pipework for different refrigerants like CO2, HFC, HFO blends, HFO. So it's going to be a great series, and hopefully you get a chance to stick around and attend all of them, as well as invite some friends. Invite some people that you know to come to these sessions, because there's a lot of value going to be here, a lot of knowledge that you can bring back to your work that is going to make you better, make your teams better, and help you all grow. James, let's get this kicked off.
I think I'll just add that the session I'm really looking forward to is maximizing system design, maximizing for energy efficiency. So in the UK, we've seen some horrendous electricity cost increases over the past 6 months, and one retailer in particular used to pay 12 months ago 12 pence per kilowatt hour. That was the lowest that I was aware of. Now a typical cost is 22.4 pence, and that's due to increase up to around 28 pence in October. So for me, the great thing is about White Rose software, we can actually MicroPipe, we can tease and reduce line penalties, and ultimately those line penalties will equate to pounds or dollar savings. They may not seem huge savings, but when you consider the new rate of energy and the fact that some systems, will last 10, 15, even 20 years, I'm really excited just to show what the software can do, as opposed to designing, not using the software. So really looking forward to that. As I'm looking forward to all sessions. So I'm going to start to share my screen now and kick off through the presentation.
Let's do it. And if you have any questions, please shoot in the chat. This is the opportunity to get those questions that you don't always get to ask experts like James. And please use the chat. Shoot me a message if you need to. Awesome. I see your screen perfectly, James.
Perfect. So I'm going to kick off just as I always do in all these sessions, for the benefit of anybody joining who hasn't been on any previous. So about White Rose software. So the software was developed by the late Ian Ramsey. It's been the choice of refrigeration system design for over 30 years in the UK. So a little bit of background for everybody about Ian Ramsey. A real genius, a complex man. He was the best mentor I've had, and I built up a great relationship. We lived really close to one another. He was quite an old gentleman. We used to go out every 2 weeks for something to eat, a few drinks, had a really, really good rapport. I learned so much off him. When he passed away, the software just couldn't disappear, just couldn't die. And I was blessed to be given the opportunity by his family to carry on his lifelong work and his legacy. And it was real difficult because it's not just the software itself, it's security that sits above the software. Worked with some IT specialists, we got it up and running. You'll see tonight the software is absolutely fit for purpose, but it kind of looks 1999, looks like, and we're embarking on a really, really exciting journey where we're going to uplift the code. It's written in Visual Basic, a supported Microsoft language, and it's going to be cloud-based. It's going to be using Azure. We're going to do some really, really cool things with it in the future. But as it stands now, as I say, fit for purpose, more than functionable, absolutely indispensable for pipework designers. So conservatively, and these are based on my estimations from large industrial systems to supermarket systems to small condensing unit type systems, which we're going to concentrate on tonight, we believe that there's over 30,000 plant systems out there in the UK alone that have been designed using White Rose software. It eliminates the need to size refrigeration lines using charts, using first principle calculations. So it removes all the inaccuracies because it understands that refrigeration systems are dynamic as well. So, which has always been a difficulty. It's easy to size a single line, but when you've got multiple things going on and lots of display cases or coolers, lots of fixtures, and some of them are satisfied, some are on a defrost, some are calling for maximum cooling, just as what we've seen in the weather in the UK. I'm sure everybody's aware we've experienced the hottest couple of days in the history of the UK. And yeah, lots of systems have fallen over. I feel sorry for our technician friends out there, but they've done a great job in keeping the nation's food cold. So moving on a little bit. So the software, the line's calculated based upon user parameters. What I mean by user parameters: evaporating temperature, condensing temperature, liquid maximum and minimum temperature, superheat, and predefined system penalties. The software can be used to size suction lines, liquid lines, discharge lines, liquid drain lines, and relief and vent lines. What makes it even more awesome is that for every single line, every single circuit, you can apply the number of bends, so you can actually mimic what's going to go on in the install. So it's not just assuming it's every piece of pipework is straight. We can put bends in there, we can add valves in, so we can accurately account for real life line losses. In a matter of fact, what does White Rose software do? We're looking at a small system tonight, but if you imagine, and I'm going to concentrate on retail refrigeration, that's my background, that's my area of expertise. So if you imagine we all go into supermarkets, all the display cases configured on the walls in runs of islands, they're all piped up and connected to a refrigeration plant. So it effectively joins the cooling fixtures, so the display cases or the cold room coolers, to the refrigeration plant in the configuration on the screen there. Plant within a plant room connected to remote condensers or gas coolers if CO2, but also there might be pre-packaged units like what we're going to concentrate on tonight, so there's no need to size the discharge or liquid drain return because effectively there's an onboard condenser assumed to already been built in. The real aim of the software, away from correctly sizing line sizes, any energy benefits that we can have, it saves design engineers time. And time for design engineers, it's hard. We've all been there. I've been that design engineer early on in my career, who was working 60, 70, 80 hours every single week at certain times of the year. This software really, really helps. So moving on a little bit, just to talk about the terminology that MicroPipe uses and what you'll hear within this demonstration. Design entries, I touched on these a little bit earlier. These are user defined, so evaporating temperature. So you can set that at whatever the lowest evaporating temperatures of the connected fixtures. The superheat. we can set maximum and minimum liquid temperatures, condensing temperature, a liquid line rise in terms of height from the liquid receiver outlet. How high does that so overcome any static lift? Circuit. Oh, sorry, before that, maximum line penalties. So these can be adjusted. So we can have sort of a higher penalty, or we can really hone in and tighten those bands up, which ultimately will probably result in slightly larger pipe work, so slightly more expensive, but ultimately, if we have a tighter penalty on that system, the less.
So James, what's the advantage of being able to put all these different design entries in? Doesn't any software offer that? Like evaporator, like for an example, a software that only does a single line and you can't do all of them. Like the evaporator, what does that really do? Because I'm not an engineer and I haven't designed. If I change that, how does it affect the system?
Well, for example, Trevor, that's very much based upon the evaporating temperature that's provided in OEM literature and data. So, for example, if I take EPTA, they're the largest case manufacturer here in the UK. So, in terms of, I'm going to talk in SI units tonight, but a typical EPTA display case will evaporate if it's open fronted at -6. You know, that's its target. So effectively, if that's the evaporating temperature, the penalty, if we talk about a suction line, we seek no greater than a 2 Kelvin line loss. And what that actually equates to is if we're evaporating at -6 at the display case or cases, when we get to the plant, the saturated suction temperature, so the evaporating temperature right at your compressor rack would be -8. The great thing about White Rose software is we could set a penalty at 1 degree, at 1 Kelvin. So effectively, we're going to hit an SST of -7 and not -8. The difference in that 1 degree can be a 4% energy saving, which in a refrigeration system is, and especially when you multiply that out potentially on larger systems as well over 15 or 20 years, that can be quite an incredible saving. And as I say, I think that's on week 3 of the demos.
Yeah, keep going. Sorry, I just wanted to find out because there's a lot of different design entries there, and maybe a lot of people on here already know that stuff. So,
yeah. Well, I think we'll open questions at the end, so I'll go through and I'll actually enter the parameters. So I haven't actually done this design tonight. I usually do, but I want to go through from start to finish this evening.
I love it.
And it's only a small system. So circuit, that's just effectively, that's defined as an individual refrigeration line or a piece of pipework. The terminology of terminal, this is effectively, White Rose software assumes everything is a network. So you've got to define it as a terminal. A terminal is effectively a circuit that is carrying a load or a duty. For example, a display case or a cold room cooler. A network is a piece of pipe which carries the duty or a series of duties. Next flow path label, this is defining where is that pipework going next. If it's circuit 1, doesn't mean might not go into circuit 2, it may go into circuit 3. So everybody will see and get the impression and idea of what goes on. And quite a big one on suction lines, and we'll touch on this as well this evening, but on every single session of this 5-part series, oil riser minimum duty. Oil risers, wow, what can I say about them? It's so imperative that those are sized correctly and sized on the minimum duty as well to get that oil back, to get it out of the evaporators, get it out of that coil and get it back where it belongs, at the rack, at the compressor, doing what it should be doing, lubricating and cooling motor windings down. Effectively, if risers are sized incorrectly, what can happen, especially if we're talking a large riser or something that's carrying multiple duties, over time, technicians are going to get oil faults. Oh, I've got a compressor, or compressors have tripped on oil. Technicians are assuming that everything's been designed correctly. So how to clear an oil fault? Well, let's put more oil in the system. Hey, that fault's cleared. To go to the next site. I've actually seen the what's happened with bad design. The amount of the gallons of oil that can sit within a system is absolutely astronomical. And in worst case scenario, that will eventually remove surface area of the coil. So it will actually make the display cases or cold room evaporators have to work harder to achieve their desired temperature.
Yeah, and that's something that you don't really think of it because you don't see the oil, but it only
No,
starts
you
to
don't.
come up after a few months, you know.
This is it, Trevor. We don't have X-ray vision. We can't see into what's going on in those pipes. I can we can all visualize, or anybody who's learning will learn how to visualize what's going on, but you can't anticipate where pipework has been sized inappropriately. And this is where the software comes in. It overcomes these problems. So the aim of this demonstration, very similar to all others, so it's going to show design engineers how to apply MicroPipe to size pipework connected to refrigeration systems, in this instance, a small condensing unit system. So before you input anything into the software, you need to have a sketch. So design engineer, either by hand or using CAD software, will sketch out an isometric showing the entire pipe run. Then on the isometric, you have some information. I'd always sketch on what the duty of each fixture is, what the meter length is, and then you can start going, and number all the pieces of pipework, starting at the one furthest away from the plant and moving back towards the plant. So you can number it up. In this instance, there's only going to be 7 circuits. I've worked on supermarket systems that have had 150 circuits. And although that sounds really daunting, that actually only takes, it takes a lot longer to sketch out the isometric. The running it through the MicroPipe software, when you're proficient and you've got experience with it and you know what you're looking for once the calculation's been performed, you're looking at an hour. It's not that time intensive. So I've already been through the last bit. So duties are added onto the schematic to terminal circuits. So just to reiterate, this demonstration is going to apply SI unit of measure. And for this one, to make things interesting, next week I'm going to look at CO2 pipe design. This time I'm going to use a HFC HFO blend R448A, which, if we are using HFC refrigerant still, I hope everybody is using 448 or 449 as opposed to 404A, just due to the obvious GWP and actually lack of efficiency as well compared to newer synthetic refrigerants. So first of all, I'm going to be sizing the suction side of the system. And then I'm going to show everybody just how easy it is to transfer the data from suction to liquid. So you don't have to do individual calculations. The only time where you may do that is one of the sessions that we're going to cover, where we may have a common liquid line, where we've got independent suction we've got independent medium temperature suction group and a low temperature suction group, but they're served from a common system, say in a booster, an MTLT booster configurated pack. So following the presentation, anybody who's interested, we have design engineer guidance notes on how to design refrigeration systems using MicroPipe. They'll be provided, along with anybody interested in obtaining a 1-month free trial of the software. Please let Trevor know. We'll do introductions. I really hope that some of you want to use the software and become familiar with it. We're always on hand to do individual specialized training sessions. The name of the game is to increase the visibility of MicroPipe and increase the number of solid sound designed refrigeration systems out there. So everybody, this is where we kind of get a little bit interesting now. What we're looking at here is a simple sketch of a cold room with 2 coolers connected to a single condensing unit. So looking at the plan and the key and the keys down there, kind of self-explanatory. To the right-hand side of the key, we've got a very small isometric, so representative of the pipe run. So we can see the terminals where notionally I've applied 9 kilowatts to both connected to a riser, so vertical lifts up. And then we can see the pipe route on the sketch itself indicated in red, and then a drop down to what is assumed to be a ground sited condensing unit. To the right of the isometric, these are the user parameters, the inputs. So in this demonstration for the suction line, I'm going to be using an evaporating temperature of -6. I'm assuming this cold room's a chilled cold room, where effectively we'll be targeting maybe 2 to 4 degrees Celsius, chilled food, superheat value of 20, maximum liquid temperature 35, minimum temperature 5 degrees, and a suction line penalty of 2K. Liquid line, obviously, again, it's -6, liquid temperature 35, assuming condensing temperature 43, and liquid line rise from the base of the condensing unit and its receiver, assuming it's got a receiver, 5 meters, and a liquid line penalty of ½ degree Celsius. First and foremost, before I start, I think anybody will attest to this who's from the UK. The condensing temperature, 43 degrees, is very, very typical of what we see and what we design in the UK as design engineers. We've just come from a period on Tuesday, Monday and Tuesday, we were well over typical ambient design condition in the UK, 32 degrees Celsius. We experienced 41 degrees Celsius. We had so many systems with problems in the UK. So much product had to be demerchandised by supermarkets. The systems just couldn't cope. I'm a big believer this is an impact of climate change that's happening right before our eyes. I think just looking at that figure now, 43 degrees Celsius condensing, I think as the UK, we need to be up at 50 degrees C. I'd have never, ever have suggested that 5, 6, 7 years ago. The temperature's been absolutely insane.
Yeah, same here. I talked to some technicians in Las Vegas. I got a few guys over my training. They're like, Trevor, it's been so hot here for so long and it just doesn't stop. 18, 20 hours days. Talk to people in Eastern Canada, same thing. Just that it's nonstop because equipment is not either, it's not serviced or maintenance properly, or it's not designed for the conditions. Like, cause a lot of times I've seen it where they design it really tight to almost undersizing.
There's always the argument as well, Trevor, that, well, if we design to a 32 degree ambient, we'll be good because we're always going to have probably 25% of fixtures in a supermarket any one time on a defrost. But of course, we're trying to be smarter with defrost now, rather than just assuming defrost on a timed basis of maybe 45 minutes or 60 minutes. We'll terminate now, or we should be looking to terminate on temperature. So something might only need to be on defrost for 10 minutes. So effectively, that fixture then comes back into line of operation. So very quickly, in times past, we'd say, well, if we design up to 95% of the plant load and we've got defrost diversification to consider, we should be good. We should be able to operate above those limits. But this past week has proven otherwise in the UK. So I'm going to stop sharing this screen for a time being, and I'm going to reshare my screen for MicroPipe. Trevor, is that good? Can you see the screen?
Yep. Yeah, it looks great.
So everybody, this is what MicroPipe upon launching looks like. So you'll get a notification about the license agreement. You can view it. If you don't accept it, the software is not going to run. So by clicking accept, as I say, I'm going to concentrate on the suction line first. So this little box, the blank piece of paper icon, click on there. It's going to tell me all system data will be deleted. Well, that's fine, even if it opens a former previous project. That doesn't matter as long as you've saved it anyway, because it launches and saves just as a Microsoft product, Excel, PowerPoint, Word file would open. So effectively, I've now got a blank canvas. First thing I need to do is make sure to select the refrigerant. So in this instance, I'm going to come down. It's defaulted to R404A. I'm going to select R448. Apply settings and close. So if you look down underneath the blue bar at the bottom, to the left of your screen, so it'll tell you what copper pipework, which is pretty cool because for CO2 we can select K65, so higher gauge copper pipework, so we know that, you know, MicroPipe won't let you select in an appropriate gauge for high pressure refrigerants either. So, you know, it takes away that possible human error. So we can see it's R448A. So from the next to the suction tab, you'll see design entries. So I'm going to go into there. You see a box here. We can set for SI or imperial units. The default is SI, but we can change those to imperial, and I'll be doing that next week and run a session in imperial units for the benefit of our friends in North America. So these are the user parameters. So -6, 20 Kelvin, 35 maximum, 5 degree minimum, liquid temperature, and a penalty of 2 Kelvin. So we've put our design entries in now. So in this box here, the 3 black boxes, specifically the network, it will always be, MicroPipe will default to network unless you advise the software it's a terminal. At the moment, we've got 1 of 1. So we're calling the isometric on the PowerPoint slide, the 7 circuits. So effectively, all the trickery happens around here. So we can add in groups of 10 if it's a large system, but for this, there's no need. So I'm just going to depress that until I get to 7. So referring to the isometric that I sketched up, I know everybody can't see it at the moment, but effectively what we've got is the first circuit is a terminal. It's connected directly to a cold room cooler. So by applying T, you probably saw real quickly, I'm going to take it off again, put it on again. The duty field at the top becomes highlighted. A network will not allow you to input a duty. A network just carries the duties across. So we've got 9 kilowatts, just 1 meter. I'm actually going to allow some bends for some losses from the coil within the evaporator. Standard amount, I'm going to stick in 6 bends. I'm going to assume that there's it's got its own. I've shown a high level isolation valve. Some coolers come dressed with valves, so no problem there. I'm going to stick a valve in there. It's the first circuit, and it flows into the second circuit, which is its riser to take it out of its box to high level above the cold room. So circuit 2. By clicking the button there, it'll take me to circuit number 2. This circuit is a riser, so it's a network, but it's also a vertical. You'll see the icons here, single and double riser. So I'm going to click on single, because it's a double riser would be used if you've got a configuration of island cabinets where you might have multiple cases. Lots can go on, especially around defrost, so you need to balance and make sure you get the oil back. So by having a primary and a secondary riser, that'll help ensure you get oil back at all seasons. So we're effectively, I'm showing a 1 meter riser. In terms of bends, I'm applying 6. So we've got 3 bends at the bottom of the trap, 3 at the top of the trap. So 6. Circuit number 2 goes into circuit 3. It's a great thing about MicroPipe. This is what we can set. We can set an oil riser minimum duty here. Now, effectively, on a cold room evaporator, it's either going to be on or off. So the minimum duty, you know, you could argue, would be 100%. I'm just going to set it at 50 so we can play around with this once we've done the calculation. So I'll stick 50% in there. Moving to circuit 3. Again, I know that this is a network terminal from sketching up the isometric that I can see at the right-hand side of me. 10 meters, we've got one 90-degree bend, showing a ball valve at high level, circuit number 3, and this is actually going to circuit 7, which is the final circuit within the system. Before we get there though, we've got 3 more to add, which effectively a duplication. So we're going to the second room cooler now. So 9 kilowatts duty, 1 meter, allow 6 bends, allow ball valve. Circuit label number 4 goes into circuit number 5. Circuit 5 again, it's a riser, 1 meter, 6 bends. Circuit number 5 goes into 6. Again, I'm going to set it at 50%. Circuit 6, which is taking us from the riser to the main branch, 2 meters, 1 valve. Circuit 6 goes into circuit 7. And here we go now. We're at our final circuit, which I've applied on the isometric of 20 meters. We've got 2 bends. Circuit 7, it doesn't have a next flow path. So all the entries have been input here. So we've hit this button here to start selection. So anyone can remember the old tape cassettes and the play button? It's exactly what that is. So there we have it. So we've clicked on there, and the biggest suction pipe work, circuit 7, it's saying it's inch and eighth. Its circuit penalty is 1.19. Its maximum penalty is 1.71. So I applied a penalty of 2 Kelvin. So that means that the temperature, the saturated suction temperature would be minus 7.71. So we can actually tighten that as well. This is the great thing about MicroPipe. So I set it at 2 Kelvin. So I'm going to change that to 1.5. So everything is going to have to be below that 1.5. Let's see. There we go. It's increased that line size to 1.3 inches, but look what it's done to the maximum penalty. It's taken it down to 0.93. So its loss from that first evaporator to the condensing unit is under 1 Kelvin. So we're really minimizing losses. I'm going to go back to the start and let's see what we look like here. So at the evaporator, 9 kilowatts, we've got 1". We've got a velocity of 6.73, so I'm happy with this. The riser, and that's the difference here. So I've set it, so I'm going to show everybody what the impact would be. So recollect, it's net down from 1" to 7/8. So naturally, there's an increase in velocity. If I change that to 100%, it takes it to 1". And effectively, what it's telling me is that 60% is minimum, but it's 1 evaporator. But I know a lot of design engineers, they always like to see a reduction in size from horizontal to vertical. So I'm going to take it back to 50% as I had previously. And then we go to the horizontal pipe above. So we've got 1". We've got a velocity of 6.73 meters per second. Circuit 4, the next cooler, be absolutely a replication. 7/8 riser into 1", velocity of 6.73 meters per second. And there we go. And that is effectively a 7-circuit. That's a refrigeration system. That's how quick it takes to design a suction side for a cold room. You know, I know it's not the most difficult and most complex system, but it really is that easy. And without me talking around, I could do that in a number of minutes, you know, from start to finish. To save the software, effectively go to File, Save As. So it's quite intuitive. do you want to enter or modify project references? Well, I'll show everybody. I'm going to call this mini series demo 1, reference being suction. Put my name in there. And then it will ask us where it wants to go. So I'm going to call this mini series demo 1 suction. Save it. That's it. All saved. So now we're going to transfer the data that I've just input there from suction to liquid. So again, this is where MicroPipe really does come into its own. You don't have to start from scratch and build up circuits from 1 through to 7. So up at the top bar here, we've got data transfer. And what we're wanting to do is transfer the data from suction to liquid. So click on there. It's going to tell me all the current liquid data will be lost. That's okay, so long as you keep on saving your work. When you finish the calculation, please do save it. So we'll go there. So if we go to liquid, you'll see that there's 7 circuits already selected. And by the way, circuits 2 and 5 on the suction, which were risers, the software automatically knows that these circuits 2 and 5 respectively will be the same size as 2 will be the same size as 1 and 3, where riser 5 will be the same size as the connection to circuit 4 and to circuit 6. So we'll clear the entries first. So again, -6 evaporating, say 35 liquid temperature, 43 degrees suction, 5 meter lift, and ½ degree penalty. And this is the awesome thing about White Rose when calculating liquid lines. Hit that play button again. There you go. It's as simple as that. So we'll go to 2 and 3 will be the same. They'll be ½ inch. Real happy with those velocities, 0.6. I try to certainly at the and MicroPipe should always do this, but really worthwhile checking and really worthwhile emphasizing. In SI units, when you hit the expansion device, you do not want to be greater than 1 meter per second. It could cause hammer, and ultimately, if you read, you'll invalidate any warranties. Danfoss, for example, if you look at a Danfoss catalog or go online, it's one of the first things that it'll tell you, that do not let liquid hit that valve at a velocity of greater than 1 meter per second. MicroPipe should know this, but as I say, worthwhile checking. So circuits 4, 5, and 6 will be the same. And circuit 7, yeah, we've jumped up from ½ inch to 5/8. So again, we can actually, and what we can see is that its maximum system penalty is 0.3. I'm actually going to try fix this at ½ inch and see what happens. It'll probably tell me it needs a greater penalty. If I hit the padlock there, reduce it to ½ inch and fix it, it may not calculate. Yeah, it's telling me that the penalty, and I always put a low liquid line penalty in because I don't want to have undersized liquid lines. But if I increase that to 1 degree C now, and I run the calculation again, you can see it's accepted it at ½ inch, but the velocity there has increased from 0.7 to 1.19. Now that's actually not serving, that's not connected to a fixture, which is going to cause the valve any problem. But the problem for me with undersized liquid lines, why I always use a tight tolerance for liquid, is the last thing I want to have is an undersized liquid main, which can effectively, in the warm temperatures that we've had when we've got multiple fixtures calling for duty, you might have enough refrigerant in the system, in the receiver itself, but you just can't transport it down. It's a high velocity. It's causing pressure losses. It's causing the system to perform poorly. So I'm going to change that back now to 5/8, fix it, and it's come back and it's reduced the velocity down to 0.74. As before, I'm going to save this file. Mini series demo 1. Liquid. Keep consistency. Series demo 1. Liquid. There we have it, everybody. The system's been designed. So I'm just going to close the system down now. I'm going to stop sharing. I'm just going to open up the final page of our presentation and over to Trevor, and then open the floor, see if anybody has any questions.
I have some questions. I always have questions. For an example there, you upsized the line, the suction line, and you went from, you had a 1.63 maximum penalty and it went down to a 0.8 maximum penalty in that line. What efficiency gain would you get from that? And do you know, because you've been doing this for years, because adding a larger suction line costs more money to the job.
Absolutely.
Would that penalty drop overcome over the total life cycle of that system by having a larger suction line in that application?
Without doubt, Trevor. I mean, what we need to, the pressure loss that's really, the penalty that's really important is the penalty that you add as the design entry. So on a suction group, for argument's sake, if I set my penalty to 2 Kelvin, that's what the system's going to work within. If you put 3 Kelvin, it's going to work within that. If you put 1 Kelvin in, it's going to work in that. And you're absolutely right, Trevor. The implication of that on a larger system, it might take your largest suction pipe work going back to your rack header from 2 5/8 to 3 1/8. That's going to cost more money. But ultimately, if we've managed to tighten the expectation and reduce the expected line penalty by one degree, for argument's sake, we can assume that I work on 4%. Some people maybe say 3%, but so say 3 to 4% saving for every degree that we can squeeze. So we're effectively do everything as engineers and technicians to keep the suction pressure as high as we possibly can and discharge pressure as low as we can. So the software really does help and support energy efficiency through reduced system losses.
And we're going to dive into that in week 3 anyway. We got a question in chat, how the limits apply to this tool, who sets the limits. So the end user, you as a user will set those limits for velocity, pressure drop. You were just talking about that, correct?
Yeah, those design criteria may often be set by a customer. So if you're working for, say, a large end user supermarket, they've got refrigeration specialists who work within their business, and they more often than not, have a comprehensive refrigeration specification. So they will actually state what the target velocities should be, what the superheat should be, what the design condensing temperature should be, and the liquid temperatures. But if not, that comes down to designer engineer experience. ASHRAE is always a good source, or DOSA as two fundamental reads for design engineers. But say if somebody was using the software and wanted to use it and run show, I'm on hand. I'll gladly assist where I can, no problem whatsoever, because there are going to be instances, and there are for me, for when I might not be looking at designs for a large user of refrigeration. I might be looking at something very similar. I've done it previously for people who've got small cold rooms, farmers, for example, butchers, these businesses, they don't have any specifications. They're relying upon the refrigeration provider to be that expert.
Yeah, exactly. We've got a couple of questions. What would the recommended velocity on a gas cooler supply and return on a distributed DX CO2 subcritical system? Do you know that?
Yeah, I effectively, what I always try target in SI is 10 meters per second on a horizontal line and 15 meters per second on a vertical. But again, you know, it's each to their own. If I was to look at the British Refrigeration Association or ASHRAE, they'll have different values. I mean, one of those two, you know, suggests, you know, over 20 meters per second in a vertical pipework. Hey, nobody's right, nobody's wrong. But from me knowing the software, what I know in terms of how I try to select pipework and design is for maximum efficiency. So those are kind of values that I work to.
Yeah. And that's one thing about CO2, the benefit to get a higher pressure, you can move that oil. Oil's not as big of an issue going out into the system, from what I know, because of the pressures. Where when we get low temp systems, you know, you're running at really low pressure. But with CO2, you're running 200 and 400 psi, or, you know, 20 bar and 30 bar, right? Or I should look those numbers up to be
You know,
accurate.
Trevor, I'll just to add to that, I think, you know, I'm really agnostic. I think there's a place for all refrigerants, bar HFs. I think there's place for HFOs. There's obviously a place for naturals, but a big advantage of CO2, you've hit the nail on the head. One thing as a design engineer, you've got no glide with those refrigerants, so that's another plus. But when we're talking about you know, there is the pressure we've got to overcome, and it is daunting, and you do have to apply extra layers of caution. But for a design perspective, I'll tell you, in all the CO2 systems I've designed, I've never had to use a double riser, no matter how much duty, because it's always going to return oil. Even if it's just a couple of fixtures on a big island run in a supermarket, you know, you've got, even if you had a really poor defrost schedule, it's still going to get it up, because we're looking at, as you say, you know, 20, 30, 40 bar in the suction line. So you're always going to get that, you're always going to get the oil coming back up on the inside of the pipes. Plus the pipes are smaller.
Yeah, and it's unbelievable though. I've done this training with you a few times, and we did this, but it's crazy how quick you can design a whole system, and the difference between using a software like this that you can do multiple circuits and from doing with charts. And I'd love to see people in the comments if you still use charts or if you use a single line software right now, is that those penalties, like how much time does it take to figure out going back when you have to change one of those pipe sizes? So, you know, that terminal 6, if I change that from a 7/8 to an inch and a 1, what does that do to all the, you have to go back into the charts, or you have to go check each one again, where this in the software, every time I've seen it, it's, you know, it accounts for the whole system, not just that one section. What do you say to that, James?
I mean, Trevor, I think with, you know, I've been doing the job a long time, and I could probably, you know, a lot of engineers would probably do as what I would if they didn't have the access to the software. You could probably size a refrigeration system without even looking at charts, because you've got that experience. For me, one of the biggest benefits of the software is, once you've saved a calculation, you print it out. It looks a bit like an Excel spreadsheet, really. You know, it all prints out on an A4 page. What's brilliant about it is, if there's an issue that might occur, it could happen during installation or commissioning, and quite often as well during installations, you know, where a designer says, I want to run a pipe down here, or she wants to run a pipe down there. Yeah, the problem is, you get to site, oh, there's a steel in there, or there's ductwork there, I can't run it, I'm going to have to route the pipe work around. So you can actually go back in very easily, increase the meterage, apply more bends, and get a realistic overview. But where I was going to come from, if there's a problem in 6 months, 12 months down the line, a service technician can say, I've got a problem, you know, and it's, even if it's not pipework related, it could be an issue with the plant, condenser, whatever it is, but at least a quick check can be performed. You know, a technician could pick up the phone and say, who's the designer on this system? Can I speak to that person? And it's a real easy check, especially when you've printed it out. First thing you'd look at, okay, my maximum duty is this, these are my velocities, these are my pressure losses, this is the overall system penalty. And hopefully the system's been designed well, because it's software at the end of the day. It's going to react to inputs. It's going to tell you when there's a problem, but it's not going to compensate for absolutely everything. But just in that instance, Trevor, I mean, if you've got a possible problem with the sizing of pipework and it's been used using charts, going back retrospectively and looking through records, if the records are still there, but more so the time it would take. Whereas with the software, it can literally be a 2-minute job just to go through and quickly analyze what each circuit and the outputs are.
Yeah, and that's one of the biggest things. You're saving time on the front end doing it, and then on the back end, if you have to do any research to find the stuff.
Absolutely.
I love that. There's another question in the chat. Is there a means or a general guidance in the tool on how to size a flash tank?
No, there's not. That's a good question. No, there's not. No, it's purely pipework. But we did say, I started off at the beginning, we're going through a period of modernization. So, and I would encourage anybody, any ideas, drop a line in the chat, or, you can see the presentation that will be distributed, contact myself and Trevor, because all these things are, great ideas. Another one being not so common in the UK, although I've had to design this morning a hot gas defrost system. And the software doesn't actually allow you to do it, because in the UK, we're so familiar. I mean, most chilled medium temperature systems defrost off cycle now, but frozen systems, we use electric heaters, where in the US and other countries around the world, hot gas defrost is actually a real thing. So that's something else I'm going to be looking at as part of the remodernization and development.
Yeah, that's awesome. That's all I've worked on is hot gas. I've worked on off time and electric, but I think it's 90% hot gas here in Canada. So, James, once again, I learned a ton of stuff just on how quickly you can size a system. There are only 7 circuits, or 7 pipes, but that was real quick. Really appreciate the time. If anybody does have questions, you can shoot them in the chat. You can always reach out to me or James. You can see our contact information up there, info@refrigerationmentor.com or info@omega-solutions.co.uk. We're really here to help. Really want to help you get better. You can size it more efficiently and be able to provide better value for your customers at the end of the day and show them this. And I think that's the key that you said there, is that you can print this off in a nice document, put it in your package, and share it with the contractor or the end user or whoever you're working with.
Absolutely.
Any final thoughts, James?
No, all I've got to say, I always enjoy running these sessions. It's always good to engage, and thanks everybody for the questions. Thanks for using your time. I know how precious time is. So thank you for joining me and Trevor, and hope to see everybody in the subsequent sessions over the next 4 weeks.
Yeah, so a next session is going to be the impact of incorrectly sizing refrigeration pipework and how the design software removes this problem. So I'm excited to learn about that, because more and more I'm hearing about sizing issues out there, or adding systems to a system that's already loaded up. And let's get another box on this system. Let's get another case on this system. So next session is going to be awesome. So James, I want to thank you very much. I want to thank you everyone for joining, and we'll see you at the next MicroPipe training. Thanks everyone.
Absolutely. Thanks everybody. Bye-bye.